Fellow students, Assalamu alaikum. Welcome again. This is the third online lecture for the course CS-241 Machine Learning. It is the fifth lecture overall, considering the first 2 weeks as your two lectures. So I hope you guys are understanding the topics. By the way, we are going to have an online Q&A session soon, inshallah. Okay, today's topic is a system of linear equations represented by ax is equals to b. So let's jump start the topic. Okay, so system of linear equations. Represented by ax is equals to b. So we are going to discuss situations where the system is unsolvable or where it is not easy to solve. So we cannot always have exact solution, or you can say where we have the number of equations equals to the number of unknowns. So we cannot crop the system to make it solvable, because every part of the system contains the information that is important. So let's first categorize the conditions or the situations where we can place the cases where the system is not easy to solve. So the first case is the underdetermined case, where we have more unknowns and less equations. So if you remember, where we discussed the case of a simple equation of a line in xy plane, where we showed that this line 3v1 plus 4v2 is equals to 1. Now this is a single line, single equation with two unknowns, v1 and v2. So we can represent it in the matrix notation as you see in equation number 1. So in this situation, exactly the case, I have taken this from the previous lecture, because since it's, you guys know it very well, so I'll just explain it so that it's a revision, as well as in the previous lecture I did not categorize that condition, whether it was underdetermined, whether it was overdetermined, or whether it was an exact. So now I am discussing the system of linear equations. So this system actually comes under underdetermined system of linear equations. So in this situation, as you know from lecture number 4, that you have infinitely many solutions. So we have to select a solution that is minimum in terms of a particular norm that we are going to select. So we'll see each and every situation in detail. The next is the overdetermined case. Now the overdetermined case, we'll see in the next slide, that it is when you have more equations and less unknowns. So in this situation we don't have a solution, a single solution X that solves the system. So what does that mean? We are going to see that exactly as well. So a single X, when we say that we have a solution, we have a solution means that a single vector X solves the system. So when I am saying that there is no solution to the overdetermined case, that means that I cannot produce the same B that is on the right hand side. So that means that B is not in the column space of A. We are going to see that shortly. So this is an example of an overdetermined system. Let's look at a similar system that we studied in the first 2 weeks. So now here I have written the three equations, and you can see in the equation number 2 I have written it in terms of matrix. Now you can clearly see the number of rows in matrix A are 3, representing 3 different equations, and the number of unknowns are 2. So in this situation there is no vector X that solves the system. So what does the other explanation, now there are two explanations to it. The first viewpoint is, let's take all these equations separately. That means I'm talking about a row wise view. So a single row represents a single equation. So when we plot these equations of lines together in an xy plane, we are going to see that they intersect each other, but all three of them do not intersect simultaneously at a single point. So this tells us that they don't have a solution, they don't have a common solution. The word solution explains, actually refers to a common solution. By the way, you can use the Desmos online tool to plot all of these three equations, and you can see it yourself that they don't intersect at a common point. Now the other view is the column view. The column view is what we are going to follow, and we have been looking at since the first lecture. So let's take the columns of vector A and see how they appear and what is the column space. By the way, this system that I have taken as an example have independent columns, and let's see where the vector B lies. Now in this figure number 1, you can see that the column space is represented by a rectangle. This depicts an infinite plane. So actually there are no boundaries, as I have told you before, but in order for you to visualize, considering this the upper line of the column space, consider it as the horizon. Okay, so it's an infinite plane, and at this side also it's an infinite plane. So if we have a solution, that means all the three equations intersect at a unique point, then the B that is produced is also in the column space. It should lie on the plane of this column space, just like the column 1 and the column 2. But this is not the case. So we don't have a solution X that produces a B that is in the column space. So B lies outside the column space. So this is the actual B. Okay. So we are going to look at this separately and treat it in a deeper way. Okay, now the exact solution. Now exact solution is when you have the same number of equations and unknowns. So what does this imply? It implies that you have a square matrix A. So when you have a non-singular matrix A, which means that it has independent columns and hence it is invertible, then we can easily find the unique X by inverting A and multiplying it by B. So geometrically, if you want to look at that, let's see an example. So I have taken two equations of lines. You can represent it in the matrix notation. So when you plot the equations separately, you can see that this is the common point where they are intersecting. So this common point is what you get when you solve this system of equations. So you take this matrix A and invert it and multiply it by the vector B. So you get the vector X, which is the solution. So let's look at the if in perspective of L2 and L1 norm. Now consider, for example, if you have a L2 norm, so the circle of L2 norm, if you keep on increasing and look for the first point where both of these lines intersect, is this. So this length is the solution vector, which is represented by 0 2 2 0, sorry, 2 in the X and 0 in the Y. By the way, for this specific case, if you use the L1 norm, you'll get the same solution. So you increase the diamond size and it will look for the first intersection point, and when it touches this right side of the diamond, it touches this is the solution. So we'll look at some other situations as well. Okay, let's discuss the least square solution. So this lecture is going to emphasize on the least square solution, that is the L2 norm of the system. Okay, equation 1, let's take the underdetermined case first, and we'll go into the detail of this. We'll take the same situation, same equation 1 that we have gone through, and we are going to study that in detail a little bit. So a system represented by equation 1 has infinitely many solutions. What does that mean? Let me revise that. So you can see the green vector from origin to the point where it touches the system, that is represented by the red line. So the point where it touches the line is the point that is on the line, so it is a solution. So when you put v1 and v2 in the system, you can solve that system. So you'll get a left, you'll see that the left hand side will be equal to right hand side. Now let's make another vector from 0 to this point. So any point on this line will be represented by a vector from the origin. So you can have infinitely many points on this line, because this line is not limited to this scope. This line is infinite. So you can have infinitely many vectors that solve this system or this line. So in the underdetermined case, you have infinitely many solutions. So the least square solution in this case would be to find out the vector that has the minimum length or the minimum L2 norm. We have seen that. So when we start increasing the radius of the L2 norm, the first point where it touches to this line is the least square solution. So this minimum length is basically the radius of the circle, L2 norm circle. By the way, this L2 norm or the least square solution is also perpendicular to the system. So there is a very elegant proof for this, but it's out of the scope at the moment. So if I get time, I'll show you the proof. It's very beautiful and very simple. So let's imagine it in R3. R3 means now we have another axis, a third dimension. So in a third dimension, this norm would be represented by a sphere, and this line would be represented by a plane. So you keep on increasing the size of the sphere until it touches a point on the plane. So that point would be the least square solution. So that point could be in case of a single equation. So since we are talking about R3, so we have a vector space of 3 dimensions. That means we can maximum have 3 unknowns. So to keep it underdetermined, we can have a single equation of plane, or we can have 2 equations of plane. So in case of 2 equations of planes, this L2 norm will look at a point where these 2 planes would intersect. So definitely where 2 planes intersect would represent a line. So all the vectors that would solve this intersection would be the solutions. So we are going to select the minimum length vector. Let's look at the overdetermined case. Now the overdetermined case, in order to understand that, I have to explain it with an example. Now since you know we don't have a solution to this ax is equals to b, but before I move forward, let me just explain. Now this is a matrix notation. Here this equal sign doesn't mean that the left hand side is equal to the right hand side. This is a compact statement. This statement contains a system of equations, more than one equations. So when you talk about a single equation, then the equal sign represents that the left hand side is equal to right hand side. But when you represent this system in a matrix notation, then this equal sign just represents that when you have an exact solution to the system, then it is equal. So in our overdetermined case, this means that this AX is different than this B. As we have seen the B coming out of the column space, if you remember in the last figure, we'll see another figure here. So that means if I take this B on the left hand side and I subtract the AX and B, definitely I'm not going to get a 0. I'm going to get some non-zero value. So what this system solution, what does the least square solution does in this case is to calculate a vector E that has the minimum energy, okay, or the minimum L2 norm. So let's look at an example. A practical example is the Hooke's law, where you apply stress and in response you get a strain. So the left hand side, let's take the left hand side as the theoretical part. This gives us the response, the theoretical response, okay, and this, the B on the right hand side, this gives us the actual empirical response what we are getting in the lab. So both of these, when you plot them, they will follow a trend, a theoretical trend, but actually they will not be, they will not represent a linear relation. The trend will be linear, but the actual relationship will not be linear. So the subject of optimization theory is applied, where it works in order to minimize this error. So it's going to provide you a solution to this system that will produce the minimum error. So in our case, the B vector, which you have seen before, does not lie in the column space of A. So any solution X must produce a vector AX that is on the column space. By the way, AX is equals to B. That means if we have an exact solution, the A multiplied by X, so we have the combination of the columns of A that makes up a B. So in an exact system, the B lies within the column space, just like this C1 and C2. So if I take any X vector and multiply it by A, I'll get a vector that is within the column space, parallel to the column space, parallel to C1 and C2. So you can see these are two examples. When I take some random x naught and I multiply it by a, I get a vector, and that vector is lies within the CA. Let's take another vector x1 and multiply it by a. So whatever I get is a vector that is a linear combination of the matrix A, and it should lie in the column space. Now, what is the least square solution? Now the least square solution is actually the vector AXI and its distance from B, the minimum distance. We have to select this vector E. There are a number of vector E's. So we have to select a vector E that has the minimum length. Minimum length means that the difference AX minus B is small. When this difference is small, that means AX is close to B. Okay, let's talk about the projection. What is a projection? Okay, with respect to this figure, let me give you an overview. If I turn off the lights here and put a torch on top of this vector B, so I'll get a shadow of this B vector down here on the column space. If I move the torch here, I'll get a shadow here. If I move my torch here, I'll get a shadow here. So I can have multiple shadows, okay, and those shadows are actually vectors that are in the column space of CA. So I have to select a vector x, a random vector x that minimizes this E. So I'll select a vector x that is which generates a vector E that is perpendicular to the column space. Now, if any vector E is perpendicular to a vector AX naught, which is in the column space, that means this vector E, which is the red dash line, will be perpendicular to the whole column space. That means any vector AX or AXI would be perpendicular to this vector E, which is the smallest length, because this is the only vector which is perpendicular. So we have to select that X that makes this error perpendicular to this vector. Okay, so let's say we have denoted X naught or X optimum to be the vector that generates a vector in the column space that is perpendicular to E. Okay, so let's take a overdetermined system and let's derive an expression for the solution X optimum. We know that the error E, if it's perpendicular to the vector AX naught in the column space, then their dot product or the inner product would be 0. As we have discussed it before, that the cosine theta would be 90, so the answer would be 0, simply 0, when we take the inner product of two vectors who are 90 degrees apart. So assuming that, that means the any vector in the column space, as I told you, is perpendicular to the error vector. Since one vector is perpendicular to error E vector, so any vector in the column space would be perpendicular, because E is perpendicular to the column space now. So any vector within the column space would be perpendicular to E. Now let's open this E. E is actually AX naught minus B. So E is made of X naught. Otherwise they won't be perpendicular. Okay, so we are selecting E that is made from X naught. Okay, so the dot product, inner product, I have shown you before. So this is represented by a row and this E is represented by a column. So we can have a product. So let's open the brackets. So AX transpose times AX naught minus AX transpose times B. Now when we open the transpose, we just change the just swap the location. So X transpose times A transpose multiplied by A times X transpose minus X transpose A transpose times B. So we can see that X transpose can be taken common. So we are left with this vector. So it is clear that X transpose is 0. So we are left with this. So if we solve it for X naught, we are going to get this expression. So if you solve this expression, you are going to get an X naught that produces the minimum error vector, minimum length error vector. Okay, so let's look at an example. So this example actually solves the system that was represented in equation number 2 earlier. So let's just place the values of the matrices and the vector B. So A transpose is nothing but the transpose of matrix A, which is the columns becoming the rows. So since this is a 2 by 3 and this is 3 by 2, so we can have a product. So this, the answer would be a 2 by 2. So this is the answer, but this is the inverse. So we in the next step we have taken the inverse as well, and we can multiply A transpose by B. Since this is 2 by 3 and this is 3 by 1, so we can have a 2 by 1 vector, which is this one. So 2 by 2 multiplied by 2 by 1 will get a 2 by 1. So this is your answer, X optimum, X O or X naught. So this X naught does not solve the system AX is equals to B exactly. Instead it minimizes the error or the energy in the error or the length of the error. Okay, so hopefully I have tried my best to explain you. This is a tricky topic, but the solution, since we don't have an exact solution to overdetermined system, so we are going to take a solution that minimizes the error or minimizes the distance between AX and B. This is actually obvious as well. So you can solve this same example in the MATLAB as well by this command. You just write A and backslash B, so you'll get X similar to this. You're going to get exactly the same answer. So behind this, it's going to solve it similar to this form. Okay. So we at this point we are going to end this lecture. Now we will be discussing in every lecture some aspect of the machine learning, specifically deep learning. So in a deep learning system, to be precise, we are going to solve the underdetermined system, and where we have more weights or more unknowns than the inputs or the system of equations. So we will be looking for, we'll be facing infinitely many solutions, that means, and we are going to look at a solution that will provide a generalized framework for our system. Generalized framework in the sense that when we train our neural network, we are going to first train it with the training input, and then we are going to select the weights or the solution X in a way that when we apply the test data, it gives us the optimum solution. So we are going to discuss that in coming lectures. So I hope you understood today's lecture. So let's meet in the next lecture soon, inshallah. But before that, we are going to have a Q&A session. I'll post it on the learning management system. So stay tuned. Thank you very much.